Let's take a look at this synthesis target. And this is an open-ended problem, so we're not given a starting material, but we are given some potential sources of carbon. So remember, these rules are going to be pretty much standard throughout this semester. We can start with benzene, and we can start with alcohols that have one functional group on them, as long as R has between 1 and 5 carbons. So that's how we're going to get our carbons. Anytime you bring in a carbon source, it has to come from benzene or a monofunctional alcohol of up to 5 carbons. So let's look at this molecule. We have an ether here, and we have a 5-membered ring. So maybe this 5-member ring came from cyclopentanol. That means that probably we need to figure out how to make that bond. Remember, with epoxides, when we add an epoxide to a nucleophile, we're going to add at least 2 carbons, and we'll end up with the nucleophile attached to one of those carbons and an oxygen group attached to the other carbon. It'll initially be an OH, but eventually we could oxidize it to a ketone or change it to an ether, which is what we have here. And you'll notice that 2 carbons away from our ether is the 5-membered ring. So what if these 2 carbons used to be an epoxide? Let's look at the retrosynthetic analysis here. What if I had this Grignard, which I can easily make from the alcohol, and I had this epoxide? If I reacted these 2 compounds together, I would expect the Grignard to react at that position, popping open the epoxide, giving me an alcohol right here, which would be here, and then eventually I could turn that alcohol into an ether. So I think these are 2 good synthetic targets. And of course, I can make this cyclopropyl Grignard from the cyclopropanol, or cyclopentanol. Sorry, I'm mixing up my P parent chains from cyclopentanol. 2 steps to the Grignard. So the question then becomes, how do I get this epoxide? Well, we know how to make epoxide, so let's give ourselves a new synthetic target here. This compound has 1, 2, 3, 4, 5, 6, 7 carbons in it, so I can't start with this. Otherwise, I could just take an alcohol and make this alkene. How can I make this compound from an alcohol, or from a smaller compound? We could envision this alcohol, because of course we could eliminate that alcohol using probably a large base to make sure that we get the less substituted alkene, although I would argue that there's really only one possible alkene isomer that we get. These methyls are equivalent. We don't have any hydrogens here, so there's only one elimination product that we could get from this alcohol. So if I have that alcohol, I can make the alkene, I can make the epoxide, and I can make my product. Can I get that alcohol from smaller pieces? Well, again, this is an alcohol. Anytime there's a C-C bond right next to an alcohol, I can create that from the appropriate carbonyl and the appropriate Grignard. So let's do that. If I have acetone, I could react T-butyl Grignard with acetone, and I would have my product. And of course, I can get acetone from isopropanol, 1 step. I can get T-butyl Grignard from T-butanol, 2 steps. And then I have, let me just circle these in red so we can identify them. That's a 5-carbon alcohol. That's less than a 5-carbon alcohol. And that's a 4-carbon alcohol. So I think that my synthetic pathway is done. So let's draw this from the front way. I saved enough space here, so I will switch colors, and then we will draw this synthetic pathway in the forward fashion. Let's start with isopropanol. And I'm going to try to snake my way up the page towards my product. Your synthetic pathway does not have to look super great. If you feel like redrawing it after you get to it, that's fine. As long as it's legible and understandable by me, the grader, I don't really care which direction you go. I'm going to try to work my way back to the product so that I don't have to redraw the product. Just a method of being lazy. So let's look at this. I need a one-headed arrow, and I can oxidize that with PCC. I now have my ketone. I need to make the T-butyl Grignard, and I can make that through this alcohol. HBr would be a great way to make the requisite bromine, because there's really not much else for T-butyl alcohol to do in the presence of HBr. And then I can just add magnesium in ether, and I have my Grignard. Mixing the Grignard, first step, second step, H3O plus, gets me to, so you want to try to draw it the same way, gets me to that alcohol, which is this one right here. I can eliminate the alcohol. I probably could use H2SO4 and do an E1 dehydration type elimination, but I'm going to tosylate. That should be pyridine. And then I'm going to add a large base, just to make sure that I get no substitution here. And that should give me that alkene, and I can make the epoxide from that alkene. This way. And now my epoxide is ready to react with this Grignard reagent. First step, second step, H3O plus. And I can get that Grignard reagent from the alcohol, PBr3. And then I can add magnesium, and I'm just going to be kind of sloppy here, but basically we get the cyclopentyl Grignard reagent. So I've mixed those together. I expect this arrow push, I'll use red here just so I can keep track of things. I'm not going to draw a lot of the mechanisms during my synthesis, but sometimes they help me keep track of which bonds I'm forming where. So let's go ahead and draw this now. And then the cyclohexane would go right over here. And let's just double check everything. I've got 5 carbons from this cyclohexane, that's the 5 carbons here. We've got these 2 carbons between the cyclohexane and the T-butyl. That's the 2 carbons of the epoxide, the methyl, and then the OH after I protonate by using H3O+. Now my last thought would be, maybe I could use this OH, actually an O-, with ethyl chloride to do a Williamson, right? SN2, here's the nucleophile, attack the carbon, lose the chlorine to make this final product ether. Now that looks great, except for one problem. This is a tertiary alkoxide, much like tertiary butoxide, and we know that that does not make a good nucleophile. This would be an even worse nucleophile, being a little more hindered. So it's likely to be a very slow reaction, or it might do elimination and simply make ethene right here instead of doing the alkylation. So let me go back to my OH. Let me get rid of that. So I got my OH. There's another way we could add the OET group here, and that's via sort of a hydration of an alkene. So if we could eliminate to make an alkene, we could tosylate this. We could use DBU to eliminate. And we could get the more substituted product, and that would be this one. So now I have an alkene here. If I were to protonate this, I'd form a cation here. I could add ethanol to that. Sometimes, though, using a strong acid, so that's what I'm trying to get at here. A strong acid with ethanol. That strong acid might react with other parts of the molecule. In this case, it's not going to be a problem. There's only one functional group here. But I would like to try to train us to avoid using strong acids if we can, just so that in the future, if there were some other thing of interest down here, it might be acid sensitive, we wouldn't have to worry about that we could solve this problem without acid. So what we could do is use another method of basically hydration, one that doesn't involve or prevents rearrangement of cations. We're not going to form the cation. We'll use mercury diacetate. And we'll use ethanol as our nucleophile here, and that will add right to the more substituted carbon, just like water would. So that's our first step. And then our second step, I'll squeeze in down here, is NaBH4. That helps us get rid of the mercury, and that leaves us with our desired final product ether. So again, when you are trying to make an ether, yes, we can use the Williamson ether synthesis, but in some instances, like this one, we might end up with a very non-nucleophilic alcohol, or once we deprotonate it, alkoxides. We may want to think about another way to make that ether, and that might involve an alkene adding an alcohol using the hydroxymercuration reaction, or alkoxymercuration in this case, or potentially you could use sulfuric acid to protonate the alkene, forming a cation here, adding the alcohol that way. Let's take a look at this chloride here. We're going to use the same rules that I wrote on problem number 1, benzene and alcohols of up to 5 carbons, so I won't rewrite them here. But the only functional group we see here, of course, well, the benzene, but the more interesting functional group is this chloride. And we can make a chlorine from an alcohol. So I'm going to go ahead, I'm going to abbreviate this phenyl ring, and I'm going to redraw this with an alcohol in place of the chloride, because I can take SOCl2, turn that OH into the chlorine, and then I have the product. And now, if I look at this alcohol, I've got a couple of carbon-carbon bonds that could be produced via a Grignard reagent. And if I cleave this bond here, you'll notice there are 5 carbons above it, so I could start with that piece, that alcohol. And then there are a number of carbons below it that I would then have to make with this aromatic ring here. So I'm gonna cleave at the bond indicated by the double or the red dashes. And if that's a Grignard reaction, I would need this aldehyde. And I can make that aldehyde, of course, from the alcohol. And I would also need this Grignard reagent. I'm going to draw the phenyl ring here. And of course, my Grignard reagent can come from the bromide. And that bromide could come from an alcohol or an alkene. Because this is in the ether or epoxides chapter, I'm going to try to use an epoxide to make this compound. So if I recognize that this bond needs to be produced, because the limit is starting with benzene by itself, so I'm going to have to make this bond at some point. If I recognize that this bond then has a carbon and another carbon after it, and that second carbon has a functional group on it, that's very indicative of maybe using an epoxide to ring open and end up with a functional group on the second of our new carbons in the chain. So let's go ahead. I'm going to cut this bond. Well, actually, first I'll recognize that this compound could come from an alcohol. So I hope by now you're realizing that when you have a bromine or a halogen, that's the same as having an alcohol. And when you have an alcohol, aside from a tertiary alcohol, that's the same as having a ketone or an aldehyde. This tertiary alcohol actually could come from this ester. The only problem is, at this stage in your chapter reading, we don't know how to make esters. So we could do this. And I'm going to erase this because this isn't useful for this chapter, but you could eventually create this ester and add 2 Grignards to it. So let me get rid of that. And let's think of a different way to do that we already know how to do. Like I said, the red line could indicate a bond that is created. So let's make phenyl Grignard. And let's make an epoxide with that other piece. I know how to make phenyl Grignard from benzene. And I know how to make this epoxide from the alkene. And I can make that alkene from couple of different, sorry, that's not what I want to do. I can make this alkene from a couple of different alcohol starting materials. I'm going to start with T-butanol, and I just have to eliminate it. And so if I look here, I have T-butanol as a legal starting material, I've got benzene as a legal starting material, and I've got this alcohol as a legal starting material. So I'm going to pause my video and erase all of my retrosynthetic arrows. You can pause your video and redraw all of these intermediates, and then we'll together fill in the required reagents to go in a forward direction. Okay, I'm going to start with tertiary butanol and turn that into the alkene. I can do that probably two different ways. I could do that with H2SO4, doing an elimination, dehydration. This typically requires heat. Or I can tosylate, and the second step would be then a large base, probably to ensure that I get only elimination happening. So either of those is fine. I can make isobutylene. Then isobutylene can be turned into this epoxide, MCPBA. That's pretty straightforward. And then I can react this epoxide with the phenyl Grignard. That's the first step. The second step would be H3O+. I can make the phenyl Grignard via, I'm just going to show this over here, Br2 Fe Br3, and then adding magnesium, and I could make phenyl magnesium bromide, which is, of course, what I have right there over the arrow. So I've made my phenyl Grignard. I now have this tertiary alcohol after ring opening the epoxide. Again, I could sort of draw some arrows to help me remember how this works. I'm going to get the ring opening at the less substituted side because I'm using a strong nucleophile. I can change my tertiary alcohol into a bromine, PBr3, and I can change that bromine into a Grignard through magnesium, and I can react that Grignard with this aldehyde. So the first step here is, of course, mixing the aldehyde and the Grignard. Second step, H3O+. I can make that aldehyde from the 5-carbon alcohol via PCC. And I can make the final chlorine species via SOCl2. I would like to point out that if you wanted to go further in this synthesis and make a more complex molecule, you could take this alcohol, turn it into a bromine, make a Grignard here, or you could oxidize it to get a ketone and add a different Grignard. You could even eliminate this alcohol, forming an alkene right here, making an epoxide, and ring open that with some nucleophile to make a more complex functional group. There are many different options, and I'm sure there are other ways to synthesize this product too, so maybe you can come up with a second or third option and share that with your classmates. All right, here's the third problem for this video. We're asked to make this compound, and we'll observe that there are two functional groups in this compound, and that's a very good indication that at some point we may have ring opened an epoxide, which often leaves us with two functional groups that we can deal with in subsequent reactions. So let's start to take this apart a little bit. The ether is easy to make from an alcohol, but if I want to make the ether last, let's say I decided I wanted to do this. How would I know which of these alcohols would react in a Williamson ether synthesis? Now this alcohol is a little more exposed, so it might be easier to deprotonate, might be easier to get to react, but I bet you we're going to get a significant amount of this alcohol either reacting in place of this one or in addition to this one. And so I don't think I want to make that ether as my last step. I want to make that ether at some point when I don't have any competing reactions that might occur. So I'm going to erase this because I don't think it's going to work very well. Let's look at another option. The alcohol here, of course, has, this is a secondary alcohol. We've got two CC bonds next to it. We could make either of those via a Grignard reaction. And this ether, I'm liking this ether as coming from an alcohol at this position. And if I'm making this bond via a Grignard, that sort of gives me like two functional groups there. So I'm going to try to make this bond. I could certainly make this bond if I wanted to, and maybe that could be your alternate synthesis pathway for this molecule. But I'm going to try to make this bond here. And This is not without pitfalls, but I think we can work our way through it. So what if I had a Grignard that looked like this, and I had a carbonyl that looked like that? I could mix those together, and I would eventually get that alcohol. So let's look at the carbonyl first. How do I make the carbonyl? Well, that has 6 carbons in it. So I can't start with the 6-carbon alcohol, right? I can't do this and say I'm done. Because there are, let's see, 1, 2, 3, 4, 5, 6. Just make sure I have the same number here. Okay, I didn't add any by mistake. That's good. All right, so I have a 6-carbon alcohol, and of course I can't start with that, but I could make this bond via a Grignard reaction. If I want to add 1 carbon to a Grignard, remember that we can use formaldehyde. And if I use that 5-carbon Grignard, which of course I can get from this 5-carbon alcohol in 2 steps, and I can get this formaldehyde from methanol in 1 step. So these are both legal starting materials. Let's circle them in red so we can keep track of them. So I'm done with that portion of the project. Let's look at the other portion. Of course, I can make this from the bromine version, and you'll notice 2 carbons have 2 different functional groups on them, and they're adjacent to each other. This species could have come from this compound. And I think I can get this, I'm thinking that I can get, that's not it, I added a couple extra carbons there. Let me try that again. So if I ring open that epoxide, can I get the bromine on the more substituted position? If I use bromide as an anion under basic conditions, right, if I just have bromide, I would expect it to attack that position. That is not what I want. What if I used HBr to affect this transformation? Could I do this with HBr? Remember that under acidic conditions, the epoxide is protonated, and then we would attack either the tertiary position, if available, because that would have the largest partial positive charge on it, or if there is no tertiary position, as in this case, the bromine would still attack the most available site. And so I don't think that I'm going to be able to make this bromo alcohol this way. Remember, there's another way to make bromo alcohols. Let me erase this failed portion of the pathway and see if there's a different way to make this. We can make bromination in water from the alkene, and we would get an OH and a Br. But again, I think that we would have them swapped. So let's take a look at this again. My thoughts here are Br2 in water. Will I get this product? And remember that from semester 1, we learned that the OH ends up on the more substituted side. So that's going to put it on this position. So this isn't going to work so well either. So maybe this synthetic target isn't going to work. I wonder if we could choose a new synthetic target. What if I made that bond? And that would mean I would have this alcohol I could turn into the bromine, and I can make this alcohol via the ring opening of this epoxide under basic conditions with a nice nucleophile. So if I use this nucleophile, that should ring open that epoxide for me, affording or providing this alcohol, which I could turn into a bromine and ultimately a Grignard. So I like this pathway better. And I can make this Grignard, of course, from the alkene, and I can make that alkene from whatever alcohol I wish. That will give me a 5-carbon chain with an alkene on the end. So we can try 1 pentanol. You could probably use 2 pentanol, although I think there's only 1 alkene possible from this one, so I like that one better. So I'm going to circle that because that is a legal starting material. And ethoxide is adding carbons, so let's just be aware of that. Ethoxide is not a legal starting material, but I can make ethoxide via deprotonation of ethanol, which is a legal starting material. So just so that we are aware of that. The ethoxide in this case is acting as a nucleophile. It's adding carbons. So I'm going to go ahead and erase all the large retrosynthetic arrows, and then we will look at this reaction from the forward direction. Okay, now from the forward direction, let's start with the 6-carbon aldehyde synthesis. We know how to turn this 5-carbon alcohol into a Grignard. So the first step, PBr3. Second step, adding magnesium. We know how to make methanol into the formaldehyde. We can just use PCC. I can mix those two together. So first step would be to mix. Second step would be H3O plus workup. That gives us this 6-carbon alcohol, which I can oxidize to form the aldehyde with PCC. Let's go down to the bottom and start with the 5-carbon alcohol. I can eliminate that. I think the easiest way to do that is probably tosyl chloride, pyridine, followed by, let's use a large bulky base so that we don't get any nucleophilic action going. We don't want any substitution. That will produce this alkene. Of course, MCPBA will produce the epoxide. I can make ethoxide from ethanol via a couple of options. I could use sodium hydride, or I could use sodium metal. That should be a 0 right there. Let me try to erase that. I can use sodium metal. So if I just dissolve or add sodium metal into ethanol, that sodium metal gives up an electron, which then reacts with the OH bond, producing hydrogen gas and an alkoxide. And then I can use that alkoxide in synthesis. So I will just mix, I'll mix my epoxide with the alkoxide, and then I'm going to add some acid as the second step to protonate my alcohol. Then I can turn my alcohol into the bromine with PBr3 and magnesium, and then I can mix these two together and follow that up with H3O+. So that is one possible strategy. You saw that while we were trying to figure out how to get these two functional groups on here, we had to go through a couple of different iterations of epoxide ring opening, and that may be true for many of your syntheses. I encourage you to think about the regiochemical outcome. Will this work? If not, can I think of a different way to do it? And you saw ultimately I decided to bring in this OET as a nucleophile as opposed to trying to make the ether by alkylating an alcohol at this position. So there's a couple different ways to do things, and be sure that you have an open mind when you're going about this. So I encourage you to think of alternate pathways here, bring them to your instructor, see what they think about it, trade them with your classmates, and work on these together.